Okay, we have a couple things that we didn't quite finish up on Wednesday's lecture, and then we will move on into the next topic of class. Oh, by the way, all right, so on the course CD and on the course website, which are identical right now, some teachers are calendar people, and some teachers are list people. Some teachers want to know exactly every day what they teach, and some teachers just want to have a big list of things. As long as they get through it all, I don't care. In case you haven't been able to tell from people who take classes from me, I'm a calendar person. Every single day I know exactly what page we're reading and all that kind of stuff. But that's what I'm behind on as far as figuring out for this class exactly what they were doing. So, for now anyway, both the course CD and the course website just have this giant list of topics. Okay? So you'll just go here to the giant list of topics. By the way, I'll leave the part. Okay. And, for example, today we'll be doing observing sea surface temperatures, so you'll go to that webpage and all the outlines and stuff are here, your PowerPoint presentations are here, any handouts you need are here. Okay? So it's just sort of topics. You'll just sort of have to go in here and get through the topics and find what you need, okay? Eventually, each of these will be onto the calendars and outlines. You'll be able to go onto here, but that's what I'm behind on. I haven't exactly decided what they were learning about El Nino and what they were learning about storm surge and whatever. So, anyway. So that's where you'll find that stuff. It's very much not the way my brain works. My brain works very well with calendars. It doesn't work with lists. Okay. So let's just sort of wrap up what we were doing. I'll just use this here rather than the board. A question that nobody challenged me with, but undoubtedly was on all of your minds. That is, why the hell are we taking this class? Why is it that we actually have the course? We talked about the fact why there's a separate course, but not why it's required. Okay? An atmospheric science degree, it's a required course in our department. Why do we require it? Well, I'm going to tell you that there's going to be a handful of reasons. These aren't really like take notes about it type reasons. These are more like how to keep you from, wondering why you're in this course. But I would say the main reason we do it is because it broadens your exposure. Pretty much all the other atmospheric science courses that you're going to take are going to be about mid-latitude meteorology. Heck, they're probably even about middle United States meteorology, right? You hardly even ever get to learn anything cool about, say, the Santa Ana winds, or European weather, or polar meteorology. I mean, realistically, we're pretty Midwest-centric in our education. Okay? So you get a chance to be a little bit broadened here. Tropics are full of interesting and unique weather, things like hurricanes, El Nino, Madden-Julian oscillations, monsoons, that you just don't see in other parts of the world. It's nice to get a chance to apply the things you learned in other courses to get to the tropics. Tropics have a huge influence on the mid-latitudes. As we'll learn in this course, the tropics are pretty much the source of moisture for the world. As the trade winds blow across these huge open expanses of the ocean, that's pretty much where evaporation happens. Okay? Pretty much all the rain that we get in the Midwest comes from the tropics. The moisture does. The tropics are the heat end of the heat engine that is the atmosphere. This is where we apply the heat, and then we dissipate it in other parts of the atmosphere. If you don't know about heat engines and stuff, you will later in other courses. And also, frankly, the tropics are just too big to ignore. Over half the surface area of the Earth is between 30 degrees north and 30 degrees south. So, it's just too much space to ignore. There's too many important things that can happen in that much space. All right, now, we need some kind of ways to define what we mean by the tropics. This is something that various textbooks and so on, including the book that you guys had, Chapter 1. By the way, did anybody have trouble getting to Chapter 1? You all were able to get those documents that I sent you? Yeah, okay, great. If you need another chapter for the next set of readings, I'll send it to you. I haven't looked at the page numbers yet. So anyway, tropical meteorology textbooks need to spend time figuring out what do they mean when they say the tropics. And it turns out there's whole different ways to come up with definitions of different parts of the world. It would be really nice if we could use a geometric definition. This would come to us from astronomy and Earth-Sun geometry relations. And that would be telling us a geometric definition would say that the tropics are the region between the tropic of Cancer and the Tropic of Capricorn. 23.5 degrees north and 23.5 degrees south. And that would be really neat. And that's not an entirely arbitrary, silly thing, because the area between 23 degrees north and 23 degrees south has one very interesting and unique thing going on. It's the only places where the sun can be directly overhead. The sun can't be directly overhead at 40 degrees north where we are. It's never directly overhead at the poles. Now, other interesting things happen in our parts of the world, or polar regions, but only from the Tropic of Capricorn to the Tropic of Cancer can the sun ever be directly overhead. So it's not an entirely silly way to define things. On the other hand, clearly tropical weather can happen in parts of the world outside of that region. So it's a good start. There's good reasons to think of the tropics as being that region, but it's not necessarily what we're going to want to work with in this class. Kinematic definitions are the kinds of things that you learned in your intro class in the unit that they probably called general circulation. We're labeling areas based on the kinds of winds that they experience there. You learned this in general circulation parts of the intro class when you learned about like the trade winds, or the horse latitudes, or the doldrums, or the westerlies, or the polar highs. You were describing areas based on the winds that were there. Okay, so kinematics has to do with motion. Okay? So you can have these kinematic definitions. And so you could say that, for example, the tropics were places where there is easterlies at the surface. Then you could say that, because I mean, generally speaking, that's true, right? The tropics are generally going to have trade winds or easterlies. We can then say that maybe the mid-latitudes are the places that are dominated by westerlies at the surface. And this kind of falls right out of there. You could talk about the subtropical highs being in between the easterlies and the westerlies, and this would all kind of work. And it's kind of the way we learn things in intro. On the other hand, plenty of places in the tropics don't have easterlies. The Western Pacific, you started learning a little bit about the Western Pacific with your reading from Volume 2 today. Western Pacific, you'll soon see, has some westerlies in it. Okay? It's also the warmest open ocean waters in the world. It's also the original region where El Nino originates. It's clearly tropical. So clearly this kinematic idea, it doesn't exactly work. But I like this idea of using the weather to describe what we mean by the tropics, but kinematic definitions aren't so clear as to how to make that work. When we're talking about climatic definitions, this is the kind of definitions that are based on how the climate influences the environment. That's not a very good technical definition, but it'll do. The best example of this is the so-called Köppen-Geiger system. Now, depending on what semester you took intro, you may have learned all about the Köppen-Geiger system. If so, that's the only time you'll ever learn it. But it's this whole business. I probably have some maps here, actually, that are examples of that, where they sort out the climates of different regions based on the plants that live there. This was actually a brilliant discovery by Dr. Köppen in the 1800s. He realized that we would never have enough climate stations out there, enough weather stations, to be able to describe the climate. Right? I mean, no matter what, even if we had a really great record from the Omaha airport as to what the climate is there, that really doesn't tell us what the weather is like in South Omaha. The climate is like, right? And if we really had it, even if we had stations in South Omaha, that doesn't tell us what Midtown is like. No matter what, there would never be enough stations. They would never all be calibrated the same. Dr. Köppen's amazing discovery, or realization, was plants are a measure of the climate. And so he developed a system that uses the plants that live in a place to describe the climates. And these are these famous maps that you've undoubtedly seen before. These are horrible black and white copies from an intro textbook, but they'll jog your memory. There were these diagrams that sorted out the world into Köppen's climate systems. They were A, B, C, D, E, and H, if I'm not mistaken. And, like the tropical climates were A's, and the arid climates were B's. Let's go to Africa here. It's got some nice B's there in the Sahara. C's are the muggy climates. D's are like northern forests and steppes and things like that. E's were the Iceland. This is a very smart way to describe climate. Okay? I mean, if a palm tree lives there, it's pretty tropical. If a cactus lives there, it's pretty arid. You don't need a weather station there to tell you it's an arid place. There's a cactus living